Okay, in the name of God. Hello everyone. How are you? Are you fine? Welcome to the class. Let me to start our lecture. I hope your friends as okay. In this lecture, I want to talk about basics of graphs and how we can use graph structures in software testing. In this chapter 7 of my textbook, there are several concepts, but you are familiar with those concepts earlier, and especially we talked about them in chapter 2 by some examples. So I hope we have a quick review. We have a quick, usable quick review on those concepts. This part of structures, or 4 structures that I talk to you is for this session and extra, I think 2 or 3 more sessions. Graphs can be extracted from different sources, such as source code, such as specification, such as design structures, design models, or can be derived from use cases. So there are various sources that we could extract graphs and use these structural graphs for generating test cases. So graphs are the most commonly used structure in software engineering, especially in software testing. And there are some different sources that we can derive graphs from those sources. We can use control flow graph, which could be extracted from source code to show the structures, the execution passes of our program. We can extract graphs from different design models, such as activity diagram, such as state chart diagram, such as sequence diagram, and we could use these graphs to show how our program behaves with special inputs. Another form of using graphs is using the finite state machine. As you know, finite state machine especially is a graph or graphs in which we have some locations and some transition between those locations, and this structure, this possibility are used in very different ways in software engineering, and we could use these structures in software testing also. Another sources of graphs, as I told for you, is using use cases. As you know, each use case have some scenario to define the functionality, to define some functionalities of our product. So the scenarios, we could make some graphs to show all possibilities, all passes of executions in our programs. Tests usually are intended to cover the graph in some way. You have experienced before in chapter 2 especially that we use a control flow graph for generating our test cases, and we have defined some coverage criteria such as edge coverage, node coverage, and edge pair coverage, and we have talked about how to cover these coverage criteria, or how to define test requirements according to each of these coverage criteria. So we have a small experience about using graphs from, at least from chapter 2, and this is not difficult for you in concepts of this chapter. Is not so difficult for you. Okay, this slide illustrates a formal definition of graph. As you know, a graph generally in mathematics is defined by a set of its nodes and a set of its edges. Okay. In this context, we have two extra modules in this definition. The first module defines our initial nodes, and the second one defines our final nodes in the graph. So please note that a graph has a non-empty set of nodes. The set of nodes should be non-empty, but set of each could be empty, could be an empty set. Excuse me, I turn off the mic for a moment. Excuse me. The first condition, structure be a graph, is that the set of its nodes should be non-empty, but the set of our edges could be an empty set. And in this context, the set of initial nodes also be non-empty set. Should be not non-empty set, and this is the same for final nodes. Final nodes also is a non-empty set. So by this definition, we check this structure. Is this structure is a graph? As you know, the set of nodes is a non-empty because there is Excuse me, can you hear me? Excuse me, our connection was lost for a moment. Can you hear me? Okay. I'm sorry. as I told, our then set n is defined by just one node. So this is and this could be a non-empty set for this structure, and this node also could be also is an initial node, because we have an entrance edge. So the n0 is defined by just this node, and this is also a final node, because we have a thick circle for this node. So this shows that this node is also a final node. So this final node is both initial node and final node. So there is no problem with these three modules of this definition. And as I told, the set of H could be an empty set. So this is no problem for H. Therefore, this is a graph. This is a graph. And the answer is yes. Set of edge, as you know, each edge consists of two nodes. One is the source node, and one is the destination node in directed graphs. Also, in this context, we name the source node as predecessor and the destination as successor node. Okay. This is another example, and these concepts are familiar for you. I hope there is no problem by these concepts. In this graph, this box says that write down the initial and final nodes and the edge. This is a graph because the set of nodes are non-empty set. It has 4 nodes, 1, 2, 3, 4, and there is an initial node, which is the node labeled by 1, and this is a final node. So there is no problem with all parts of the definition. The last part of the definition is the set of edges. We have 4 edges in this graph. So this is a graph with this description. This is this formal description of this graph. This could be saved in memory. And this is another graph. In this graph, as you saw, there are 3 initial nodes. 3 initial nodes. We have 3 initial nodes, 1, 2, 3, and we have 3 final nodes. It's possible in a graph that we have several initial nodes and several final nodes. Suppose we have a program in which we use the return statement in several locations, in several statements of our code. Okay. In a, for example, in a program that we could have several methods, and each method could be a final method and use a return value, or in a single method, it's possible that we have several branches. We use, for example, a switch case structure, and in each case of our switch case, we use a return statement. So in this piece of code, we have several exit points. So there should be as several final nodes. So in this graph we have this description. In 0 is this set, and final nodes are these nodes, and all edges of this graph are listed in the set E. And this graph, this structure is not graph. Why? I say that this structure is not a graph. Why? Because in this structure we have no any initial node. The initial node is marked by an entrance edge, but in this graph we have no any entrance edge for none of its nodes. So this is not a graph structure in our context. Look at this description. Because the N0 is an empty set, so this structure is not a valid graph in our context. You are not the definition of pass, but as you see, the formal definition is stated in this slide. The pass is a sequence of nodes. Each subsequent nodes in this, each pair of these nodes in this sequence makes an edge. Each pair of nodes in this sequence should be an edge in my graph. So a path is a sequence of nodes. A graph could be defined by no path. A graph with a single node, as you saw, is a valid graph in our context. Length, the length of path, is the number of edges located on that path. A single node is a path with length 0. This is trivial. A subpath is defined by a subsequence of nodes in each path. A subpath is defined by a subsequence of these nodes from this list, from this path. So it's clear. I think it's clear for you. In this graph, we have several passes. A path could be node 1 to node 4 to node 8. Another path, node 1 to node 5 to node 8. Another one could be node 1 to node 5 to node 9 to node 6 to node 2 and to node 5. This is another path. To node 8, there is no problem to repeat any nodes of the path at the end of any path. So some of these passes are listed in this box. This is a, for example, look at the second path in this list. This could be a path started from an initial to 5 to 9 to 6, and this structure defines a loop. in our context. Suppose there is no need to start each pass with an initial node. In the definition of pass, this is not a valid precondition to start each pass with an initial node, or there is no with a final node. So the pass could be started from an arbitrary node. For example, we could define this edge as a path, this edge from node 7 to node 10. Or we could define this edge as a path from node 6 to node 2. Okay. Test pass. A pass that starts an initial node in an initial node and ends at a final node is an execution pass in our programs. A pass starts by an node and ends at a final node is a complete execution path of our. So we could say that this is a test path, because we could have a complete example, a complete execution of our program. So test passes represent execution of test cases. For example, in this graph, this is a simple pass started by a simple test pass started by node 1 and then go to node 3, go to 4, go to 6, go to 7. This is a test pass. Also, this is an execution pass because it starts with an initial node and ends at a final node. So this is an execution pass, or this is a test pass. By some test values, by some input values, we could experience this execution pass. So this is a test pass. Some test passes can be executed by many tests. What's the meaning of this sentence? Some test passes can be executed by many tests. This means that we could experience this execution pass by several test data. For example, in a addition program, the addition of 2 and 5 and the addition of 5 and 8 both uses the same test pass, uses the same execution pass. Both could be run by the same execution pass. So there are several input tests, input values that control our program to behave as this pass, to experience this pass. So each test pass could be executed, by several test values. Some test passes cannot be executed by any tests. What's this test passes? And infeasible test passes could not be executed at all. Why? because there are no valid inputs to feed the program to behave as infeasible. What is the infeasible? Could you tell me, can you tell me an example of infeasible test pass? Suppose we have some nested branch. For example, let me to type for you in some place. For example, we have a code that have a branch if, excuse me, my keyboard don't type. I can't type. Enable editing. Excuse me. Suppose we have an if statement in which its condition is x less than 0, and in the body of this if statement we have another branch if x is greater than for example 5. It's obvious that, excuse me, it's obvious that any statement that located which is located in the body of this if statement, such as x b x times 2, it's clear that this statement could not be executed at all, because this is an infeasible if conditions. X could not be less than 0 and at the same time x be greater than 5. So if we have such these structures, this could define a branch, some branch in our graph, but those branches are not an invisible, are not feasible branches. We could not find any input for x to reach this statement. This is infeasible. This would be infeasible execution pass. Okay, so there are passes in our graphs that are infeasible and could not be executed at all. Okay, so some test passes could not be executed by any tests. Another concept in this slide is single entry, single exit graph. For example, this graph, assume this is a control graph. This control graph is SE graph, single entry, single exit graph. In single entry, single exit graph, all test passes start at a single node and ends at another node. Okay, we have single entry and single exit. So M0 includes just one node, and this is the same for NF, final set. Final nodes have exactly one node. So the description of this, in the description of this graph, we have just one initial node and one final node. Look at this, 4 test passes. All of them started at node 1 and all of them are finished at node 7. Another 2 concepts are described in this slide. The first one is visit concept and the tour concept. A visit concept says that a test pass P visits a node N if N is located in pass P, in the pass P. This is the same for, could be defined the same for visit edge. A test pass P can visit edge if an edge E is located on the pass. This is trivial, this is a clear definition. And the tour, what is a tour? A test pass P tours subgraph Q of P if Q is a subgraph of P. This is clear. For example, in this test pass tours the subpass which start from node 2 and end at node 5. This test pass visits the edges 1 to 2, 2 to 4, 4 to 5, 5 to 7. This is all edges of the set of all edges of this pass. And this pass visit, for example, the node 4, visit node 5, visit node 7. Okay, these are clear and I think there is no problem to explain. And there are some subpasses of this pass that what's the meaning of pass T? Let T be a test case, be a test. Okay, if T be a test, so there is an execution pass that could be toured by this test case. So the test pass executed by the test T is showed by pass T. Each test case has only one test pass. In deterministic software, each test case tours just a single test pass. But in deterministic software, by a test case, we can tour some different test passes in different times, because in the indeterminate software we have a random behavior. So by a single test case, we could not execute, we could not have the same execution paths in different times, in different executions. Okay. And path of T, the capital T, is the set of test cases. If T define a test, the capital T defines a set of tests. So for capital T, we have several test passes. One test path for each test case. So path of capital T defines the set of test passes executed by the set of tests in T, in the set of T. Each test executes one and only one test pass, as I told for you. Complete execution from start node and final node, it's clear. A location in a graph, for example, node or an edge, can be reached from another location if there is a sequence of edges from the first location to the second one. It is clear and there is no need to more explanation. If you have a question, please ask your question. But there are two different terms in this context, a syntactic reach and a semantic reach. A syntactic reach defines a subpath in the graph, but a semantic reach means that there is a test to experience a subpath, to execute that subpath. But it's possible to a node or an edge from a graph be reachable syntactically, but it could not be necessarily reachable semantically. It's reachable semantically if and only if there be a test case to execute that reachable test path, reachable subcase. Okay, so a node could be semantically reachable if there is a test to execute the related subpath. Okay. The last item said that the distinction becomes important in section 7.3. We use this distinction in that section. The relation of tests and test passes is shown in this slide. This slide emphasizes that in deterministic software, always test always executes the same test case. If we execute this test 1 many times, all of those executions execute the same test path, and it's not independent to time, to other factors. But in non-deterministic software, a test may be executed via different test passes in different times, because the behavior of non-deterministic softwares are randomly, and the behavior is dependent on, for example, when we want to run the software. Its behavior depends on extra factors other than our test values. For example, in non-deterministic software, we could have some branch which depends on a random value. For example, in meta-heuristic algorithms, you know that there are different executions for the same input value, and we could not repeat the same execution path by one test case several times. Okay, so in deterministic software, each test case execute just a test pass, and there are several test values for the same test pass. But it's not so for non-deterministic software. In this course, we focus on deterministic software. Testing and covering graphs, these terms are familiar for you, and there is no new concept in this slide. We use graph in testing as follow: develop a model of software as a graph, such as done for control flow graph in chapter 2. Require tests to visit or tour a specific set of nodes, edges, or sub passes. This statement defines the test requirements. As you know, the test requirements are defined by our coverage criteria. Okay, if our coverage criteria be, for example, node coverage, our test requirements are a set of nodes that should be covered by our tests. And you have experienced in this concept in chapter 2. Test requirements is defined as TR, capital T and capital R, describe properties of test passes. For example, describe nodes that should be covered. Describe edges that should be covered, or prime passes or simple passes that should be covered, or edge pairs. Test criterion is defined in chapter 2 also as rules that define test requirements. We use test criterion to define our test requirements. As you know, if the test criterion is edge pair coverage, so the test requirement is a set of all possible edge pairs of my control flow graph. The satisfaction is defined by coverage term in chapter 2. Again, satisfaction given a set TR as our test requirements for a criterion C. A set of tests T satisfies this coverage criterion on graph if and only if every test requirement from TR could be covered by a test pass, in our test set. Okay, each test of this test set defines a test pass. So if each test requirement is covered by each test, we say that this test set satisfies the corresponding coverage criteria and meet the test requirement. You have seen structural coverage criteria again as a control flow defined by control flow graph, defined on a graph just in terms of nodes and edges, or edge pairs, or passes. Another approach is to using data flow graph. We could define data flow graph for our programs, which defines the location of our definitions of our variables and when they are used in our program, by defining their locations as nodes in my graph. We will explain this approach in detail in this chapter. The data flow graph criteria requires a graph to be annotated with references to variables. When each variable is defined and when it is used in the program. Each variable could be defined in some location, in a location, and it could be used in several later locations in our graph. In several test passes, it could be used in several passes of our graph. Okay. So as you know, a program could be run or could have an incorrect output if we have used an incorrect variable, incorrect value, or incorrect setting of a variable. Okay, so the data flow graph could be usable in software testing, and this defines a set of coverage criteria, and I will explain them at this chapter. Node and edge coverage is familiar for you, and there is no need to explain this slide. The first and the simplest two criteria requires that each node or each edge in a graph could be executed. Formally, node coverage is defined as test set T satisfies node coverage on graph G if and only if for every syntactically reachable node. Please note that in this definition we use syntactically reachable node, not semantically reachable node. Syntactically reachable node, and in capital N set of nodes, there is some passes in pass P, in pass T, such that P visit N. What's the meaning of this definition? You have experienced this definition a lot in previous chapters. So take it easy, and this is no difficult definition. Just the prominent point of this definition is using this syntactically reachable node. So the simple form of this definition is presented here. Node coverage is defined as TR. Let TR be the our test requirements, contains each reachable node in G. So we need a test set T to cover all these test requirements, this set of nodes. Edge coverage is defined the same, and You are familiar with node coverage and edge coverage. For example, in this simple graph, for node coverage, we should cover all three nodes, node 1, node 2, node 3, and for node coverage, just a pass 1 to 2 to 3 could cover all nodes. So by this one execution pass, by this one test pass, we can cover all three nodes of this subgraph. But for edge coverage, we should cover all these three edges, this edge, and this edge. And all these three edges, as you know, this node defines a branch. Defines a branch in which it has two exit edge. Okay, so we could not cover all edges by a single test pass. This test pass just cover these two edges, and we need another test pass, say this, to cover this extra edge. So for edge coverage, we need two test passes. The test requirement for node coverage is this set is defined as this, and a test pass to cover, to satisfy this test requirement is defined by this test pass. In this case, by one test pass we could cover all nodes. And in the other case, in edge coverage, our test requirement is defined by this set of edges. We have three edges: 1, 2, 2, 1, 2, 3, 2, 2, 3. These three edges. These three edges could be covered by two test passes. So a test pass set we need to satisfy this test requirement include two test passes. Okay. Let me see your messages. No, son. Can you hear me? This message is old, huh? Okay. Can you hear me? Okay. Passes of length 1 and 0 is ordinary in this context. A graph with only one node defines no pass. A pass with 0 length will not have any edge. This is a simple graph in our context. It may seem trivial, but formally, edge coverage needs to require node coverage on this graph. What's the meaning of this item? This item says that, as you know, edge coverage subsume node coverage. So edge coverage should cover this our graph. If we define edge coverage with no node, so edge coverage will not subsume node coverage. So we define length up to 1. instead of simply length 1 for edge coverage. Okay, we define all passes up to 1, such as pass of length 0. When we execute this graph just at node 0, we experience a pass of length 0. So this guarantee that edge coverage subsume node coverage in this context. So we define length up to instead of length exactly B1. We have the same issue with graphs that have only one edge for edge pair coverage. As you know, in edge pair coverage, we should have a pair of edges for each edge pair. So in a graph with one edge, there is no pairs, any pairs of edge. No any pair of edges. Okay, so we change our definition of edge pair coverage to cover any passes of our, any subpasses of our graph up to length 2, because each edge pair has length 2. But in a graph, in this graph, we have no any pass of length 2. So we change our definition for edge page coverage so that it subsume the edge coverage. It can subsume the edge coverage, because when we say that it should cover all passes of length up to, we say that it should cover passes of length of 1. So the edge coverage, the edge pair coverage could cover edge again. Please note that in this definition, edge pair coverage is defined as TR contains each reachable pass of length up to. The prominent point of this definition is this point. It should cover all passes of length up to 2. Okay, so that it could it can subsume edge coverage. As we defined before in chapter 2, we said that edge coverage subsume node coverage because covering all edges guarantee that all nets be covered, and edge pair coverage subsume edge coverage. Because of this previous definition, we define edge page coverage to cover all passes, all subpasses up to 2 lengths, up to 2 edges. The phrase up to 2 is used to include graphs that have less than 2 edges. In this example, all edge pairs is defined by these edge pairs. This edge and this edge is an edge pair. This edge and this one, this edge and this one, all of these 3 edges with this extra edge make 3 more edge pairs. So in this graph, we have 6 edge pairs as listed in this set as our test requirement for edge pairs. Okay. Complete pass coverage is defined as our test requirement set contains all passes in graph it's obvious that for a graph with loops, the complete path coverage is infeasible, because the number of all passes are infinity. So unfortunately, this is impossible if the graph has a loop. So a weak compromise makes the tester decide which passes, and we define a specified path coverage. A specified path coverage is defined by tester. Some of those passes in a looped graph is defined as our test requirement by tester, and we name this in this state this test requirement as a specified path coverage. Sum of all infinity passes of my graph is defined by tester to be covered by our tests. So test requirement in this definition is defined as a set S of test passes where it is supplied as a parameter. S is defined by a tester. This is usable for graphs that has loop. For example, in this graph, in this structural coverage graph, we have a loop. We have a loop. There is no problem. There are no problem with node coverage, edge coverage, and edge pair coverage, because they are clear in this structure. All nodes are finite. We have 7 nodes in this graph that should be covered by our test passes. So the node coverage could be possible. This is the same for edge coverage and for edge pair coverage, but a complete path coverage could not be possible, could not be feasible, because we have a loop in this graph, and it's not possible to define all possible loops, all possible passes for this structure graph, because we could travel this loop for many times, and in any execution we have a specific pass, test pass. So the set of test passes of complete passes is infinity. For example, in this structural graph, the test requirement for node coverage be the set of all nodes of the graph, such as this set, and test passes that need for this for cover all nodes. Look at the graph. Please note that this test pass could cover some nodes of this graph. This path started from node 1 to node 2 to node 3 to node 4. This node defines a branch. So in a test pass, we can just cover one of its existence edge. So if we go to this node, we cover this node in this test pass, and so we can go to the node 7 as a final node. So this could be one test pass to cover these nodes. Another test pass could be this one, from node 1 to node 3 to node 5 to node 6 to node 5 again and to node 7 to cover all nodes as showed in this box. For edge coverage, it is easy for you and there is no need to explain more. We should cover all edges and it could be done by 2 test passes or 2 test cases because we have a branch, we have 2 branch, this branch and this one, and this one 3 branches. This loop at this location we have 2 options, so this could act as a branch. Okay. For edge pair coverage, the list of all edge pairs are listed in this set, and to cover all of these edge pairs we need many test passes as illustrated in this box. 4 test passes are used to cover all edge pairs. Please check these test passes and see if it is possible to cover all edge pairs with fewer tests. If it is possible, please write a test set with fewer test cases to cover all all edge pairs. A complete coverage pass is not possible because the set of passes are infinity. We have so many different passes in this graph because we have a loop. This loop caused this problem, and this could not be covered by any test set. Handling loop in graphs. If a graph contains a loop, it has an infinite number of passes, as I said, and complete pass coverage, CPC stands for complete pass coverage, is not feasible. It's clear. So, to handle loops, we use a specified pass coverage. We use a specified pass coverage to handle loops in graph. So we propose some test passes that cover around the boundaries of our for condition to cover all edges of loop. For example, in this graph, we use 2 or 3 executions of this loop. For example, the first one is skipping the loop. The second one is execution the loop once, and the third one could be executed twice. So in a specified pass coverage, we use, for example, this 3 execution to cover this loop, to handle this loop and escape from covering all possible passes by this tactic. Okay, the specified pass coverage is not satisfactory because the results are subjective. It's dependent on the tester belief. For example, the tester wants to test this loop once, for example, or wants to test this loop twice, for example, and it's not be so satisfactory as cover all possible passes and vary with the tester. Some attempts are done in before decades before previous decades to deal with loops. For example, some attempts is execute cycles once. For example, this cycle for previous graph for this graph, and execute each loop exactly once, formalize execute the loop 0 times, once, and more than once, or define prime passes, Turing prime passes. A prime pass is a simple pass in which there is no node repeated in the past. We will define simple pass and prime pass in this slide. Okay, let me see your message. No problem. What's a simple pass and prime pass? A simple pass is defined as a pass from node Ni to node Nj. Is simple if no node appears more than once. We have not repeated any node in our pass, in our sequence of nodes. Okay, except possibly the first and the last could be the same. The first node, for example, in a loop in previous graph, in this graph, the pass started from node 5 to node 6 and ends again at node 5, could be a simple pass because no nodes are repeated except the first node. This is a simple pass. From node 5, we start from node 5 to node 6 and return to node 5. The first node could be repeated in simple pass. In simple pass, there should be no internal loops. A loop is a simple pass. A loop could be a simple pass. For example, in this graph, this loop defines a simple pass. This loop starts from 1 to node 2 to node 4 and again to node 1 is a simple pass. But this could not be a simple pass from node 1 to node 2 to node 4 to node 1 again and to node 3. This step causes that our pass not be a simple pass. Okay. And what is a prime pass? A prime pass is a simple pass that does not appear as a proper subpass of any other simple pass. A simple pass that does not a subpass of another simple pass, another bigger, another longer simple pass is a prime pass. In other words, the biggest, the longest possible simple path is a prime path. For example, in this graph, there are several simple passes, and we have just fewer prime passes. Because some of these simple passes are sub-passes of some of these prime passes. some of these simple passes are subpasses of some others. For example, the pass from 1 to 3 is an edge. This edge could be seen in this pass and in this pass and again in this pass. So this could not be a prime pass. This is just a simple pass. An edge could be a simple pass, but it could not be a prime pass because it could be a subpass of some bigger, some longer simple passes. Okay, so we have just these prime passes. The prime pass coverage. In the prime pass coverage, we define test requirements as all prime passes of graph G. So we need we need a test set to cover all prime passes of a graph. It's obvious that prime pass coverage subsumes node and edge coverage, but it could not subsume edge pair coverage. Why? As you know, each edge, as you know from this example, each edge could be a simple pass, and each edge, if it's not a subpass of some other simple passes, it could be a prime pass. So prime passes cover some prime passes includes all edges of our graph. Okay, so prime pass coverage could cover all edges, and this is the same for all nodes. All nodes are passes with length 0. Please look at this example. We listed all simple passes. In this list, we see passes with size with length 0, in which they are just individual nodes. Okay, so prime pass coverage simply subsume node coverage and edge coverage because they could be located, they are located in these passes. Otherwise, they could be located in our prime pass set. Okay, so prime pass coverage subsume node coverage and edge coverage, but prime pass coverage could not always subsume edge pair coverage. Why? Look at this example. Let me see. Please research why not prime pass coverage subsume edge pair coverage. Please research about this. I hope we have an example in our slides to explain this problem. If a node n has an edge to itself, self-edge, edge pair coverage require, okay, this example explain that problem. As I told you, this is an illustrative example to explain why H prime pass coverage does not subsume H pair coverage. PPC stands for prime pass coverage. In this example, please note that we have some H pairs which could be started from H2 to H2 again and then go to H3, or another H pair could be started from node 1 to node 2 and then go to node 2 again from the self edge. So we have two H pairs with this description. These are two H pairs of these graphs. These H pairs are not sub passes of all prime passes, because we define a prime pass as a simple pass that have no node repeated, that have no loop, no internal loop in the pass. Okay. No node could be repeated in each of these paths except the first one and the last one. So these two H pairs could not be covered by prime pass coverage. These two H pairs just could be covered by H pair coverage. This pass, for example, is not a prime pass. So prime pass coverage could not subsume this H pair coverage. Okay. A prime pass example is shown by this graph. All nine prime passes, 9 prime passes are possible for this graph, and all of them are listed in this box. You can check these prime passes yourself, and I think I have no any time, yes, to explain this example. Please ask your questions if you have any question. We have 12 extra slides in this set of slides. Please check your, excuse me, let me go to the online video. Please check, please watch these parts of these videos. These parts, basics of graphs and structural graph coverage. Please see these two parts. This set, I sent the links for you via WhatsApp group to see for this chapter.
To reiterate at this point in my course.
I send you This is the first part, and this is the
what happens when the loop ends.
one. Structure of college. This is the second part. Please see these two parts for this chapter. Okay. If you have no question, let me finish this session. Okay, I appreciate you for your attention, and have a nice day till to the next session. Good night. Thanks a lot.